Morning, nerds, and welcome to the beginning of some of my absolute favorite mathematics, outside of logarithms, trigonometry. We are now finished with the material that we needed to learn from our textbook. We're going off the beaten path, and we're moving into the realm of trig because for those of you that I have green lighted to go into AP Pre-Calculus, you need to have the knowledge of trigonometry to be successful. Now, you should have learned some very rudimentary trigonometry in geometry. Some of you might not have gotten that far. And, well, I just simply can't let that be. It can't be that you may or may not have seen it in geometry, then you took a year off in Algebra 2 Honors, and then towards the end of AP Pre-Calc, you go, hey, remember that trig that you learned? Because the answer will be no, and that's if you even did learn it. So I'm going to start you from the jump, okay? Now, here's the thing. The key to being successful in trigonometry is understanding where it all comes from. If you are not a fan of understanding where everything comes from, and you just like to blanket, blind memorize stuff, okay. Then you will need to blanket, blind memorize everything in this image. Everything. This is called the unit circle. So you could either blindly memorize all of the information in here, radicals and pies and coordinates and degrees and all kinds of mess, or you could do trig the way that I do it. That it involves memorizing very little information. So I'm going to teach you how I know how to do this stuff. First things first. Circles have 360 degrees, right? Wrong. They don't. We just said they do. You ever wondered why we say that circles have 360 degrees? It's literally a man-made idea. We decided one day, ancient mathematicians, thousands of years ago, to say that circles were made up of 360 degrees. And the only reason why was legitimately because you could divide 360 by a lot of things. It's divisible by 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, yada, yada, yada. It's divisible by a lot of things. That is the only reason why we say that circles have 360 degrees in them. But that's what you're used to, so for now, let's talk about degrees, 360 of them, and common subdivisions of them. There's some very common fractions of circles that come up in mathematics. And those common fractions of circles are the quarters, the eighths, the sixths, and the twelfths. Okay? So what we're going to do in these images is we are going to subdivide our circles, their degree measurements, into these fractions. It's important that you understand that in trigonometry, all angles begin at what you would call the positive x-axis at 0 degrees. And then they open counterclockwise. So they're going to start like this, and then they would open like this. And they would work their way around counterclockwise. That is why our quadrants are numbered the way they are, with quadrant 1 being here, and then quadrant 2, quadrant 3, quadrant 4. Should have learned about that in Algebra 1. But that is why they're numbered in that way, because all angles begin here and then open this way, which you also should have seen in geometry. All our angles are going to begin at the positive x-axis and then open counterclockwise. Cool? All right. So as we go counterclockwise, the first quarter of a circle, well, that's 1/4 of 360 degrees. What would that be? 90 degrees. The second quarter would put me here, which would be how many degrees? 180. Everybody then is comfortable with me saying that half of a circle is 180 degrees. But did you notice how I called it the second quarter? Because 2/4 is 1/2. Okay. The third quarter would be 270 degrees. And then we finish our full circle at the fourth quarter, 360 degrees. Also, my voice is fried from that sinus infection that I came down with over the weekend. My apologies. But that's not bad, right? You ever go somewhere and have like a personal pan pizza? Like Pizza Hut or whatever? They cut them into fourths. Right? Okay. A standard large pizza, though, is cut into 8 slices, isn't it? Well, here's my eighths. What relationship do eighths have with fourths? They're half of it. So here's still 0 degrees, and here's still 90 degrees. Well, what's half of that? 45 degrees. So that is the first eighth. An eighth of a circle is 45 degrees. This is the second eighth. This is the third eighth. What is that in degrees? 135 degrees. This is the fourth eighth. 4 over 8 is still 1/2. The fifth eighth. Just add another 45 degrees. 225. The sixth eighth is still 270. But the seventh eighth of a circle is 270 plus 45, 315 degrees. And then, of course, back to where you began, 360 degrees. You know the saying, a full 360? Or to do a 360, means turn a full circle. Most medium pizzas are not considered large enough to slice into 8 slices. They are often cut into 6 slices. But what is 1/6 of 360? 60 degrees. The first sixth then is here. The next one is here. From here to here is a 60-degree angle. So there's the first 60. So the first sixth, the second sixth, which by the way is 1/3 of a circle. The third sixth is half. If you add 60 to 180, you get 240. You add 60 to 240, you get 300. So there's the fifth sixth of a circle. What a weird thing to say. And then, of course, the sixth sixth, back to 360 degrees. So you notice I didn't label the 90 and the 270. But that's because they're not multiples of 60. Make sense? Imagine they weren't there. You would have 6 slices. Like a typical medium pizza. But if you've ever been to one of those pizzerias where they've got the pizzas as, big as manhole covers, sewer covers, the extra large, they'll sometimes cut them into 12ths. And you've already said that you know that eighths are half as big as a fourth. So hopefully you know that a 12th is half as big as a 6th. 30 degrees. So we're going to go 30, oops, 60. Oh, look, the second 12th is the same as 1/6. Well, duh, 2 over 12 is 1 over 6. This time, the 90 shows up. It's the third 30. And we're just going around adding 30s. Hopefully noticing that every other one was one of the things I wrote in green. That's not bad, right? Not that scary, is it? Okay. But I just told you that degrees are a man-made thing. They're a man-made construct. Wouldn't it be better if we had some measurement system for circles that wasn't man-made? A measurement system for circles that is inherently true by the very nature of the circle? Wouldn't that be better? Yes, Ms. Brown. Okay. Scoop my computer out of the way because I need space. Time for a demonstration. This is a piece of a twisty tie. You know, like to tie a bag of bread or something. I've got it flattened out. It has some length. I don't know what that length is. But I have my compass set to be just as wide as the length of the twist tie. Can we agree to that? Compasses are used to draw circles. So I'm going to say that's the center of my circle. Picked a generic point. And without changing the size of my bow compass, I'm going to draw a circle with radius the size of that piece of twisty tie. Cool? All right. When I use a compass, I don't turn the compass, I turn the paper. I just find it easier. There. So you can see that twisty tie is the radius of this circle, yes? So thousands of years ago, when people are goofing around with circles and stuff like that, they start to realize that this circle is clearly a property of this radius. In fact, every point on this circle is exactly the same distance from the center of the circle. That's what a circle is. But it should be obvious that this particular circle is the circle created by this particular radius. And every differently sized radius creates a differently sized circle. So clearly, this length and this length must be related to one another. Yes? Okay. So we've got some people, they've stuck a stick in the dirt, they stretched a string out with another stick, they drag themselves a circle in the dirt. They then take this string and they start laying it down in the dirt, in the curve of the dirt, to figure out how many of these it takes to get around this thing it created, right? So we're going to do the same thing. I got to bend this thing so that it matches the arc of the circle to the best of my ability. That looks pretty close. That's pretty good. That's pretty good, right? I did a pretty good job. All right. So there's my first one. We pick our rope up from the dirt and we move it over. There's my second one. You know, and we just keep doing this because we're really curious. We know they're related to each other. So how many would it take? You know? That's pretty good. And, you know, it's getting to be pretty obvious how many it's going to be. You know, it's getting to be pretty obvious that it's going to be 6, right? I mean, and that should make perfect sense because 360 degrees is easily divisible by 6, right? It should make perfect sense. There should be 6 of them. So we put it on there and, you know, we're going to measure it out. We're going to make sure that it's exactly 6 because that's what we expect. And, you know, we go and we didn't hit exactly 6. Maybe it was human error. Maybe I wasn't precise enough. Maybe that's what caused this. So I dig another hole in the dirt with a different size string. And I take that string and I start laying around in the dirt. And darn it all, it still took more than 6. Try a bigger one. It still takes more than 6. And as it turns out, it didn't matter how many times we try it, it always takes more than 6. I wonder how much more. It's got to be a set number. Otherwise, it wouldn't keep showing up as just over 6, would it? So what we do is we take the radius string and we cut it in half. I'm going to fold it in half, okay? Maybe it's half. If I had a pair of tweezers for this. Crap, it fell. Okay, half is too much. Half is way too much, you know? So you cut the half in half and you get a quarter, right? And you lay it on there and dang it, the quarter is not enough. And it doesn't matter what size radius we choose. It's always more than 6.25 every single time. So we start getting more and more precise measurements, more and more precise measurements. And what happens is, it turns out every single time, regardless of the size of our radius string, it takes about 6.28-ish times around every single time. And this number is clearly part of the nature of the circle because there was nothing man-made about what just happened. I took an arbitrary radius, drew a circle with it, and then measured how many times that radius goes around. So this value, this number of radii that it takes to get around the circle must be part of the true nature of the circle, correct? Can we agree to that? So it's because of that, we give this number a name. This number is tau. The Greek letter tau. And yeah, as it turns out, there are tau radii in every single circle's length. But it becomes very clear really quickly to a lot of people that half circles are also extremely beneficial to us. Think about the archways in the Roman Colosseum and stuff like that. Your archways are half circles because they're very geometrically sound. They could support a lot of weight. It's also a good way of maximizing volume while minimizing surface area, using half circles and stuff like that. That's why, you guys know the Volkswagen Beetle? You know the bugs? That's why they're round. Because it's a way of maximizing volume while minimizing surface area. So they can get as much space as possible inside the vehicle while using a minimal amount of metal to pull it off. That's why they're round. Anyway, because the half circle is very beneficial to us, we cut this number in half. And because people typically don't want to write things in fractions over and over and over again, give this number its own name. Pi. This is how pi was discovered. Pi is not created. Pi was discovered. And that's how. You just saw me discover it, did you not? I didn't just discover that. I didn't just take an arbitrary length and measure it.
Someone made that.
The symbol is man-made. The value it represents is not. The value it represents is clearly part of the circle's nature. The word and the symbol are man-made, just like the word table. Are we arguing about whether or not words are made up? All symbols are made up, but what they represent are not. Okay? This is the symbol we chose to represent this value that was not made up. Okay? Because half circles are very beneficial to us in construction. And that's why. It's literally because of architecture, half circles are really, really beneficial. They do a lot of good stuff for us. Very geometrically strong, and they minimize surface area while maximizing volume of 3D objects. Anyway, so instead of saying that there are tau radii in a circle, we say that there are 2 pi radii in a circle going around it. It's going to take me 2 pi of them. Comfortable with that idea? But here's the thing. If you remember back to geometry, all angles are created by 2 segments, right? There's an angle. There's another one. Another one. And this angle itself, the size of this angle must be special. And why must it be special? Because it doesn't matter the size of the circle or the radius. There will always be 2 pi of this angle in every circle. There's always 2 pi of them. This angle, as you can see, is by the nature of the circle, not man-made. This is the length of my radius. This is the length of my radius. And if you remember, this curve is the length of my radius. This angle creates an arc whose length is the same as the radius of this circle. And there will always be 2 pi of this angle in every circle. And because of that, we give this angle a special type of name. This angle is called a radian. And there are exactly 2 pi radians in every circle. There's exactly 1 pi radians in every half circle. Which is what you have in this box. It is showing you this length and this length. They are the radius of the circle. And if they create an arc that is the exact same length as the radius, the measure of that angle is 1 radian. The name is man-made, but the fact that there are 2 pi of them in every circle is not. So we say there are 2 pi radians for every full circle, and we say that full circles are 360 degrees. So if you cut both those things in half, you get 1 pi radians in every 180 degrees. That means there's a little bit more than 3 of these angles in every half of a circle. This is a unit conversion. It's like converting between inches and centimeters, or Celsius and Fahrenheit. It's just unit conversion. That's all it is. Whereas this is a man-made unit, and this is the nature of the mathematics. The name is man-made. The symbol is man-made. But the number of them is not. If I asked you to convert feet to inches, could you pull it off? Like if I said to you, show me the work and turn 3 feet into inches and show me the work, what would you do? You'd multiply by 12? Oh, you know why? Because there's 12 inches per 1 foot. And anytime you divide something by itself, it cancels out. And inches is the only unit left. This is how unit conversion is done. It's called dimensional analysis in science classes. Okay, they get fancy. It's unit conversion. That's all it is. And we could do the same kind of stuff going between, back and forth, degrees and radians. So first thing we're going to do is we're going to convert 75 degrees into radians. What you saw me do on the front was cancel this unit out. This unit is technically on the top of a fraction. It's over 1. You want to cancel something that's on the top of a fraction? You have to put it in the bottom. So if I want to cancel degrees, I have to put degrees in the bottom of a fraction. And the only, what's the word I'm looking for? The only conversion that I know is that there are 180 degrees in every pi radians. Degrees divided by degrees cancels. And that leaves me with 75 pi over 180 radians. But 75 over 180 reduces. What number goes into both of those? 5 does. All right, if you divide them both by 5, what you get is 15 pi over 36. What number goes into 15 and 36? 3. You want to know something cool about radians? You ready for this? You want to hear something rad about radians? They are the default angle measurement, which means you don't have to write radians if you don't want to. It is assumed that every angle is in radians unless you see a degree symbol. So if you write an angle and there's no degree symbol, that's radians. And I can prove to you that it's the default. The calculator defaults to radians. There it is. Can I change its mode? Of course I can. But it defaults to radians. Math is done in radians, not degrees. Why, Mr. M? I'll tell you why. Because radians are small numbers. Quick! How many degrees are there in 8 full circles? A lot, right? How many people in the room know right off the top of their head what 360 times 8 is? Nobody. Could you figure it out? Sure you could. Guess how many radians are in 8 full circles? 16 pi, done. I just did 2 times 8. Rad. A radian is an angle whose arc length is equal to the length of the radius. And there are 2 pi of them in every circle. So there are pi of them in every half circle. Pi is a number. It's a little bit more than 3. So I don't need to write rad. It's assumed. This one, because there's no degree symbol, is assumed to be in radians. Let's convert it to degrees. If you want to write it, though, put it on top. Because if you're trying to cancel radians, you need to have a fraction that has radians in the bottom. But the only conversion that I know for radians is that there are pi of them in every 180 degrees. Radians cancel. Pi's cancel. You would grab handy dandy calculator and you would get 220 degrees. How about that? So that's how you convert back and forth between radians and degrees, and you'll be doing that in your homework. So you remember those 4 images on the front? Here they are again. And what we're going to do is we're going to convert all of our degrees into radians because it's better. First one was 90 degrees, correct? What is 90 over 180? 1/2. So this is pi over 2 radians. This is 0 radians. Notice I didn't put a degree mark. This is pi over 2 radians. If this is a half of a pi, then what is this? A full pi. Remember what I said? There's pi radians in every half circle. So here's 1/2 pi's, 2/2 pi's, 3/2 pi's, 4/2 pi's. 1/2, 2/2, 3/2, 4/2 pi's. I'm treating pi as the unit. It's not, but that's what I'm doing. See, half of a pi, 1/2 plus 1/2 pi's, 1/2 plus 1/2 plus 1/2 plus 1/2. Yeah, that's working. Eighths were 45 degrees, weren't they? But we said that was half of 90, right? What color was that? Purple? It was blue. Oh, wait a minute. Trying to stick to the pattern here. There we go. How many 45s are there in 180? 4 of them. So this reduces to 1/4. Well, duh. That's half of a half. Count with me. 1/4 of a pie, 2/4 of a pie, 3/4 of a pie, 4/4 of a pie. See, there's 4 slices in that pie. 5/4, 6/4, 7/4, 8/4. The faster you can let go of degrees, the better off you're going to be. Radians are where it's at, not degrees. If you asked me, where is 315 degrees? Okay, I know that's in quadrant 4. And I know that's 7 pi over 4. But if you asked me where 1,560 degrees is, I would poop myself. But if you asked me where 17 pi over 6 is, oh, that's easy. 17 over 6, that's almost 3. So this is 0, 1, 2, 3 pi. It must be here-ish. Radians are the way to go. Sixths. What color was that? That one was green. What is 60 over 180 reduced to? 1/3. Zero radians. 1 pi over 3. 2 pi over 3. 3 pi over 3. 4 pi over 3. 5 pi over 3. 6 pi over 3. So if you said, where is 14 pi over 3? I would go 6, 12, 13, 14. There's 14 pi over 3. How many degrees is that? I don't freaking know. That's a big number. But you see how fast I found it in radians. And the last one on the front, was that purple? Purple was 12ths. How many times does 30 go into 180? 6 times. Oh, duh, it's half of a pi over 3. It's a pi over 6. So 1 pi over 6. 2 pi over 6 reduces. 3 pi over 6 reduces. 4 pi over 6 reduces. 5 pi over 6. 6 pi over 6. 7 pi over 6. 8 pi over 6 reduces. 9 pi over 6 reduces. 10 pi over 6 reduces. 11 pi over 6. Notice that every other one of them was a green number. That's because every 2/30 is a 60, right? You need to know this. You need to. And to help you with that, one of the things you picked up on the way in is the reference sheet. Still see a couple pencils wiggling, so I don't want to cover these notes yet. You're going to want to keep this reference sheet in your binder. Use it until you have mastered radians. Okay? We're not going to be able to fill the whole thing out today, but we will fill out some of it. The first thing tells me to label my quadrantal angles in degrees and radians. My what? Well, these are the quadrants, right? The axes are known as the quadrantal angles. So this is, we're going to be dividing each half circle into 4 pieces. Where's my pencil? So right now the half circle is divided into 2 pieces, correct? So we're going to divide it into fourths. That means cut my halves in half. And we're going to label this thing with the degrees and the radians. What color was that first one? The first one was, well, my fourths were blue. So this is 0 degrees, but it's also 0 radians. This was 45 degrees, but it was also pi over 4 radians. 90 degrees, pi over 2 radians. 135 degrees, 3 pi over 4 radians. See, 1/4, 2/4, 3/4. 180 degrees, pi radians. 315 degrees, 3, 4, 5 pi over 4. 270 degrees, 6 pi over 4, which is 3 pi over 2. Not 350. Not 315. What's wrong with me? 225. Holy cow. I just had a stroke. This is 315 degrees. You see, I know radians so much better than I know degrees. And in this little bow tie here, we're going to do that. Now, every one of those triangles had a 45-degree angle within it. So put a 45-degree angle inside every one of them at the quote-unquote x-axis. Because we will always draw these kinds of triangles, which we'll talk about at a later point in time, with a vertical down to the x-axis. So I just drew those. I filled those in. Okay? We need to do it for the 6ths and for the 12ths as well. I'm clearly not going to get the whole thing done before the end of the video, but you already have all the knowledge. It's these with these. The next one was in green. We were supposed to cut each half circle into thirds. Ooh, okay, that's going to look like this. 0 degrees, 0 radians. 60 degrees, pi over 3 radians. So I'm just putting the two circles together on one image. This is your reference sheet. 120 degrees, 2 pi over 3 radians. Notice that the quote-unquote y-axis didn't get marked in green. I mean, it's still important. It's still pi over 2 radians. It's still 90 degrees. It just isn't one of my green ones. This is the third one. So this is the fourth pi over 3. This is the fifth pi over 3. And of course, this is 2 pi again. So again, this didn't get numbered. It's not one of my green ones, but it is still 270 degrees, or 3 pi over 2 radians. The bow ties then are these 4. And those are all 60-degree angles. And the last one, when you fill your bow tie out, only use the ones that were unique to the 30s. Don't repeat these. I'll show you that one in tomorrow's video. I'll have it done for you. Thanks, nerds.